So, hello everyone, my name is Kritik, and today we're going to be talking about the current generated by charges moving in a circle. So, I have drawn a case here to represent this situation where we have an infinitely long rod and a ball of negative charge which is orbiting it with a time period. And as it's orbiting it, it's gonna have some centripetal force that's gonna keep it in the circular motion, which is basically the electrostatic force between them, and all of this is occurring in a vacuum medium. So the values that they've given us are the charge of the ball, which is q, and then the charge density of the rod, which is lambda, and the radius of circular motion r, and then mass of the ball m. So the steps to finding the solution to this problem are finding the force at a distance r from the rod, and then we find the velocity of the ball, and then we find the time period of the revolution, and then we find the current. So as you know, the ball is moving around in a circular motion. So current is going to be the amount of charge that's flowing through a point per unit time. So if the ball takes like 2 minutes to go around, complete the orbit, it's going to be charge divided by its time period of 2 minutes. As you know, because that's how long it takes for the ball to complete the full rotation and then come back to its starting point. So step 1 is finding the force, right? So we already know charge as they've given it in the question, so we only have to find the electric field. So to find the electric field, we can use Gauss law, but before we use it, you must know what flux is. Flux is the amount of electric field passing perpendicular to the surface area and parallel to the area vector. So if you can see the if I take an example surface like this, and if the electric field is going like this, that's the electric field. It's actually perpendicular to the area, but if you look at the area vector, it's going to be in the same direction as the electric field. So if this is the electric field, this is going to be the area vector. It is going to be in the same direction, so the angle between them is 0. We take the angle between them for the cos theta here. So the formula for flux is area into electric field into cos theta, which is the angle between the area vector and the electric field, not the actual surface area, which if you might look at it, it looks perpendicular, but the actual angle between them is 0. So Gauss law states that flux through a closed surface is the total charge enclosed in it, which is the net charge enclosed in it, divided by the permittivity constant. And as this case is vacuum, I'll take the permittivity constant as epsilon naught. So as you can see, the formula here is q net divided by epsilon naught into electric field multiplied by the area vector. So as you can see, I've got an infinitely long rod here, and I've drawn an imaginary cylinder around it to calculate the electric field. So if you look at this top and bottom area here, the electric field is actually perpendicular to the area vector. So if you substitute the theta as 90 here in this equation, you're going to get 0. So those two areas are not going to generate any flux, so we can ignore them. So but if you check here, the area vector, right, it's parallel, it's actually parallel to the electric field. So the theta value is going to be 0, and if we plug it into this equation, this is going to result in 1, which is basically the most amount of flux possible in this case for this area and for this electric field. So we can ignore the top and bottom areas, and we only have to consider the curved surface area. So we can ignore this area, which is basically the top and bottom area, and this is actually the curved surface area, and we only have to consider this. And the charge is going to be the charge density multiplied by length, because as you know, density is just charge divided by length. So if you multiply both sides by length, L and L will cancel out and you'll get Q. So if you substitute all these things in the equation, Q net by epsilon naught is equal to E into area, you can basically cancel out the L and you can rearrange it using algebra, and then you'll get this equation here. So as you can see, we are multiplying the top and bottom by 2 in order to make the equation more readable and easier. So as you know, 1 by 4 pi epsilon naught is k value, so we can multiply and divide by 2 and convert this bit into k. So after converting it, this is the equation that you're gonna get. So now that we have found the electric field and we know the charge, the force is just gonna be this multiplied by the charge. So now we can move on to step 2. Now if you go to step 2, you might have learnt in lower classes that mass multiplied by velocity squared divided by r is going to give you the centripetal force. So once you get the centripetal force, you can equate the force that we had previously found here to the centripetal force, as both of them are going to be the same. So once you equate them and do some algebra, you're going to get velocity as this. So once you get velocity as this equation, we can move on to step 3, which is the time period. We have to find the time it takes for the charge to complete the whole revolution. So the total distance of the revolution is going to be 2 pi r, as the radius of the revolution is r. So the time, as you know, is distance divided by velocity. So we can take the total distance as 2 pi r, and we can substitute the velocity equation over here. If we do that and if we rearrange the terms, we will get this equation right here. So the next step is finding out the current. The current is q divided by time, as charge divided by time, as current's definition is charge per unit time, charge passing through a point per unit time. So if we substitute the time period equation over here, and then we put the value of charge q over there, and we rearrange the terms, we get this equation. So this is basically the big version of this equation over here. If they have already given the velocity, the tangential velocity in the question, you can use this equation here, which is just the total charge divided by the total time, and you can get the answer. But if for this particular case that we have taken, this is the formula that you have to use. So this is basically the charge generated by the ball over here while it's revolving around this infinitely long positive rod. So thank you for watching. This is my short presentation on how to find current when the charge is moving in a circular orbit. Thank you and bye.